Alkene. YouTube-nya udah on kan? Oke.
Okay, students, please inform all the other students to immediately attend because we will start the lecture in 1 minute.
Yeah.
Okay. Okay, students, please inform all the I think we can start the lecture right now.
Yeah, we can.
Okay, just okay. Good morning, everybody, and good afternoon for Ian there. Today we will have the second lecture series of organic synthesis. In particular, we will have about oxidation and reduction of organic compounds. Here we have already Dr. Ian Curry from Curtin University, especially for the moment, he is actually is full employed in the Walter and Alice Hall Institute. So before we start the lecture, please allow me to read the brief resume of his CV. Ian is actually got a PhD in synthetic organic chemistry from Curtin University. And the interesting one about his skill is related to our lecture today, that he has a really extensive practical experience in synthetic chemistry research. So we hope that today we will learn a lot about the organic synthesis, theoretically as well as in practice. And regarding about his publication, he just got a recent publication in Organic Letters 2021 in the synthesis of acyl phosphoramidates employing modified Sturgeon reactions. So I guess he is really expert in this field of lecture. So I hope we can learn a lot, especially for the student here. Before we start, let me remind all the students that the student can ask the question during the lecture by typing in the chat box, or you can also ask in the discussion session later on. So please, the screen and time is yours, Ian.
Thank you for the kind introduction. And thanks for the opportunity today. So yeah, with the questions, I'll leave them to the end. So if you just make a note of the slide number, we can get to that at the end. So today I'll be presenting on the oxidation and reduction of organic compounds. So this is really a vast area in synthetic chemistry, and there are numerous reactions that can be classed as oxidation or reduction reactions. So this is not really a comprehensive look at all of the reactions. This is just a focused set of reactions that really are good examples for these types of reactions. And by understanding these, you can then apply that to new reactions you may not have had a chance to look at before. So first of all, I'll be looking at the oxidation section, and then later on, I'll start looking at reduction reactions. Okay, so first of all, this slide shows a selection of oxidants that are commonly used in organic synthesis. So they're grouped into different groups here. So at the top is perhaps the simplest oxidant, which is hydrogen peroxide. So one thing you'll note about all of these oxidants is they're in high oxidation states, and this gives them their properties as oxidants. So for hydrogen peroxide, it has the oxygen in a higher oxidation state. And similarly with the peroxy acids, the oxygen-oxygen double bond has a higher oxidation state of oxygen and thereby can act as an oxidant. So you can see this is similar to all of these peroxy acids. They all have that oxygen single bond there. And then moving down is sodium periodate and other similarly structured oxidants. So osmium, chromate, and several others. And then further down is some other oxidants, also chromium-based, in addition to hypovalent iodine, and also some N oxide oxidants. And then finally is the DMSO-based oxidants. So DMSO is an oxidant that can be activated by various electrophiles shown here and can then oxidize organic compounds. So when we talk about oxidation reactions, the most, I suppose, common reaction you'll come across is oxidation of alcohols. And that's what we'll look at first. So as you may know, primary alcohols can undergo an oxidation to an aldehyde, and then they can undergo further oxidation to carboxylic acids. The secondary alcohols cannot be oxidized to ketones, and generally they do not undergo further oxidation. However, towards the end of this section, we'll look at situations where they can be further oxidized to esters. And then finally, tertiary alcohols are generally unreactive towards oxidation reactions. So it's a brief overview of different oxidants and their usefulness. First of all, the primary alcohol to aldehyde oxidation. This is known as a selective oxidation reaction, since the additional oxidation of the aldehyde to carboxylic acid is unwanted. So to get a selective oxidation to an aldehyde, you can use reagents shown here, which we'll go into in further detail later. And these are generally fairly mild oxidants, which do not oxidize the aldehyde further. If you do want to oxidize the aldehyde through to the carboxylic acid, and you start often from the alcohol and go straight to the carboxylic acid, you can use stronger oxidants such as those shown here. And then for a secondary alcohol to a ketone, you can generally use any of the oxidants shown above, since there is no issue with selectivity and it does not undergo further oxidation. And then, as mentioned before, the tertiary alcohols are generally unreactive. Okay, so first of all, the chromates are widely used as examples for oxidants. And the mechanism for the oxidation of a secondary alcohol is shown here. And this mechanism is the same for a whole range of oxidants, and you'll see similarities with this mechanism to other mechanisms shown further. So initially, the alcohol undergoes a nucleophilic reaction with the chromium trioxide to give this intermediate shown here. And then, since the chromium trioxide is able to accept a pair of electrons from this oxygen-chromium bond, then you're able to remove a proton from here, and this bonding pair of electrons moves into the carbon-oxygen bond with elimination of this chromium. So that's effectively an E2 elimination reaction to give you your carbon-oxygen double bond here, in addition to the chromium at a different oxidation state, and also removal of some acidic protons. So with chromic acid, it really undergoes the same type of reaction. So chromic acid is just the hydrated form of chromium trioxide. So you can imagine adding H2O, or in this case, OH negative to the formula here, to the chromic acid. So the chromic acid is generally the form of the oxidant that's used for chromium trioxide, and this is known as the Jones reagent. Okay, so moving forwards to Swern oxidations. So this is, there's a whole series of reactions based on DMSO, and they are all able to oxidize an alcohol to a carbonyl compound. And these are particularly useful in selective oxidation of primary alcohol to aldehyde, since under these reaction conditions, the aldehyde is not oxidized further. So for the Swern oxidation, the DMSO is activated with oxalyl chloride shown here. And this is the traditional method for activating DMSO. However, there are numerous other similar activating reagents which can activate DMSO to participate in these oxidation reactions. So some of these electrophilic activating agents are shown here. So trifluoroacetic anhydride, and N-chlorosuccinimide, oxalyl chloride, and all of these have properties as electrophiles, which are able to react with the sulfur, the oxygen on the dimethyl sulfoxide to activate it. So having a look at the mechanism, initially you have this dimethyl sulfoxide. So the way it's written here is in one of the resonance forms where the negative charge is on the oxygen and the positive charge is on the sulfur. And this is equivalent to the structure shown here, just a different resonance form. And this oxygen can then undergo nucleophilic addition to the oxalyl chloride to give this tetrahedral intermediate, which then eliminates chloride to give you your activated dimethyl sulfoxide. This undergoes further reaction with the chloride anion, which is produced in the prior step, to give you this sulfonium, the sulfenium chloride. And this is in fact the active oxidant in the Swern reaction. And also in the process of reacting with oxalyl chloride, you generate these two molecules of gas, which is common to all reactions with oxalyl chloride. So following the formation of this activated oxidant shown here, it reacts with your alcohol to give this intermediate here. And this is really equivalent to the chromium activated intermediate shown on the previous slide. And this can be deprotonated at this methyl position. And then the same as the mechanism shown on the previous slide, you deprotonate at this alpha oxygen position with removal of the oxidant. And there should be another arrow which is missing, which shows the formation of this carbon-oxygen double bond. And so you can see that you're losing dimethyl sulfide. So this is the reduced form of dimethyl sulfoxide, and you're forming your oxidized form of your alcohol, in this case, a ketone. So this is a very mild and very useful reaction for forming ketones and aldehydes. So this is another example of a similar oxidation. In this case, you're using DCC instead of oxalyl chloride. However, the mechanism is identical and is essentially identical. So first of all, the dimethyl sulfoxide is activated by reaction with the DCC, and this activated dimethyl sulfoxide then undergoes reaction with your alcohol, then deprotonation of the methyl group on the sulfur, and elimination of the elimination of the oxidant here. So again, you get deprotonation of this position next to the oxygen, and that pair of electrons then migrates to form your carbon-oxygen double bond of your product. And in this case, instead of forming your gaseous products like with the Swern reaction, you're forming your urea, and again the dimethyl sulfide and your oxidized product. So the mechanism may look a little complex, but it's really the same for all of these dimethyl sulfoxide based oxidations. So moving forward to a different type of oxidant. In this case, it is a hypovalent iodine. So you can see the iodine here is bonded to has more covalent bonds than you might normally associate with iodine. And so therefore it's called a hypovalent iodine. So the iodine in this molecule is at a much higher oxidation state than your typical iodine, which is at a -1 oxidation state. And so therefore it is quite a useful oxidant. And again, it's useful for oxidation of primary alcohols to aldehydes without further oxidation to carboxylic acids. So the reaction mechanisms shown below here. So your alcohol undergoes a nucleophilic substitution at the iodine. So your acetoxy is a good leaving group, and that's substituted by your alcohol to give you this intermediate here. So again, following the same mechanism shown before, you deprotonate at the position next to the oxygen, and that pair of electrons moves in to form your carbon-oxygen double bond with loss of your oxidant. And so therefore you form this as a byproduct, and you'll notice this is a reduced form since it has fewer covalent bonds than the starting oxidant. And you also have your acetic acid from this step here, and also your product here. So this is perhaps even more mild reaction conditions than the DMSO, since it does not require any additional base. And yeah, this is probably the mildest oxidant, and generally gives very high yields and very, very clean reaction products. And in addition, it doesn't use any toxic chromium salts and doesn't produce any unpleasant smells from the dimethyl sulfide byproducts. So this is a really good reagent. Okay, moving forward, again, for selective oxidation of alcohols to aldehydes. In this case, we're looking at a amine oxide. In this case, it's abbreviated TEMPO. So this is an abbreviation for tetramethyl piperidine N oxide. So it has this NO, which is the N oxide, and this can react with your alcohol to give this adduct here. And then, as before with the other mechanisms, you get deprotonation of this carbon position next to the oxygen. That pair of electrons moves in to form your carbon-oxygen double bond, and you get elimination of your oxidant in its reduced form. So in this case, you form your ketone or aldehyde, and you have a hydroxylamine, which is a reduced form of your N oxide. So for this reaction to go to completion, you would need stoichiometric amounts of your oxidant. However, in this case, you're able to use a catalytic amount of your oxidant in addition to a co-oxidant. So the co-oxidant in this case is sodium hypochlorite or bleach, and your co-oxidant regenerates your tempo catalyst by oxidizing this product, and it oxidizes it back to the original tempo, and this is able to participate in another reaction. So this is convenient because the sodium hypochlorite is a very cheap reagent. However, the tetramethyl piperidine N oxide is relatively expensive. So by using a catalytic amount of tempo, you're able to make it a lot more cost effective and convenient to carry out the reaction. And there's a number of other oxidation reactions that use a catalytic amount of your oxidant in addition to a co-oxidant to regenerate your original oxidant. And there'll be some examples further on of this. So moving on from your alcohol oxidations, there are a wide range of other molecules that can be oxidized, including sulfur and a lot of others that we won't have time to go into. But the oxidation of sulfur is quite common and useful to understand. So in this case, you start with the sulfide, which is the most reduced form, and that can undergo a single oxidation. Most commonly, this oxidation performed using a peroxide, such as hydrogen peroxide, which is shown here. So this sulfide has 2 lone pairs of electrons and is a very good nucleophile. And it undergoes a nucleophilic reaction with the peroxide here, and you eliminate OH, so hydroxide. And this gives you your sulfoxide. And this reaction is very fast. And when we say it's fast, it's in relation to a secondary oxidation that can occur. So the sulfoxide can undergo another oxidation to the sulfone through an identical mechanism. However, this step is relatively very slow. And due to the rate differences of this first oxidation and this second oxidation, it is quite possible to selectively oxidize a sulfide to the sulfoxide without unwanted further oxidation to a sulfone. And this can be quite useful to be able to stop this reaction at this first step. Okay, and then moving further on to oxidation of carbon positions. So one reaction that's commonly looked at for undergrad chemistry is oxidation of benzylic positions of aromatic compounds. So this can include toluene or further substituted ethyl benzene here. So toluene undergoes oxidation to the carboxylic acid. However, when there's a substitution at that benzylic position, the oxidation stops at the first step, which is the ketone. And as mentioned before, the ketone is generally unreactive to further oxidation. So these reactions occur specifically at the benzylic position since it's more activated. So this can be explained by a radical mechanism, and because they can be quite complex, it's not drawn here, but the radical at the benzoylic position is highly stabilized, and therefore the oxidation occurs at that benzoylic position, since that initial formation of a radical is favored at that position. So these types of reactions require very strong oxidants, such as potassium permanganate, sodium dichromate, or chromium trioxide. And because it's very strong and harsh reaction conditions, they don't really tolerate many other functional groups. So looking further at substituted aromatic compounds, they're not all equally easy to oxidize. So if you remember that oxidation is the loss of electrons, then compounds that are already deficient in electrons are harder to oxidize. This can be explained in a number of ways, but it can also be explained by stability of a benzoylic radical. But I think the easiest way to explain it is just that oxidation is the loss of electrons. So a compound that is electron rich is more prone to oxidation. And so this is demonstrated in the example here, where you have a methoxy substituted aromatic ring. So the methoxy group is strongly donating, making it electron rich, and therefore it's relatively easy to oxidize to the carboxylic acid. In contrast, the nitro group is very strongly electron withdrawing, and since it is an electron deficient compound, it is much harder to oxidize to the carboxylic acid. So you can use protecting groups. So this type of reaction, although it is very harsh, it is compatible with protecting groups. So in this case, this can be oxidized to a benzoic alcohol to give you your free amine. So this is an oxidative cleavage reaction. So this is one way of removing a protecting group on an amine. So in this case, the PMB group is a paramethoxybenzyl group. Because it's relatively easily oxidized, then it can be removed under oxidative conditions to cleave this nitrogen carbon bond, giving you a free amine and benzoic alcohol, which would undergo further oxidation. And similarly, the dimethoxybenzyl group is even more electron rich and is therefore even more readily removed through oxidation reactions as a protecting group. Additionally, these protecting groups can be removed under strongly acidic conditions. And this is due to the stability of the benzoic cation generated. And this benzoic cation is stabilized due to the electron-rich aromatic ring due to the methoxy groups. So that's one useful application of these oxidative cleavage or oxidation of benzoic positions. Okay, so now we're going to move from oxidation of single atoms to oxidation of alkene bonds. So the alkene bond is shown here, and just as revision, consists of a pi bond, which prevents rotation around this carbon-carbon double bond. As a result, the alkene can exist in what's known as a trans or cis configuration. So the trans is where the substituents are at the opposite sides of the double bond, and cis is on the same side. And this is important to understand for reactions of alkenes, since the two trans or cis isomers will give you different stereoisomeric products as a result. So if you look at a tri-substituted alkene here with these three substituents being methyl, then there's no trans or cis isomerism. And similarly, where all substituents are equal. But it's just good to recognize where that isomerism does exist. So first of all, one of the most common reactions of alkenes is addition of a halogen, in this case, bromine. And I know that Lydia covered some of this previously, so I won't go into too much detail with this. But this is, in fact, an oxidation reaction. And you can see this clearly by looking at the oxidation state of bromine. So because it's elemental bromine, it's an oxidation state of 0. And after the reaction, it is an oxidation state of -1. So clearly, oxidation reaction has occurred there. Furthermore, if you look at the stereochemistry of the product, the bromine atoms are on opposite sides of the molecule. And this can be shown through the mechanism. The reason for this can be shown in the mechanism here, where initially the alkene reacts with the bromine in a nucleophilic substitution reaction, and you get this carbocation intermediate. And following this, a secondary bromine, the one that's removed in this first step, then adds to this carbocation. And this addition occurs very selectively at the opposite side to that initial reaction to give you the trans product and not the cis. So understanding this selectivity mechanistically, if you look at this carbocation intermediate, it has some interaction with the bromine atom that is adjacent. And this can form a 3-membered ring called a bromonium, shown here. And this, if you remember SN2 reactions, then it will have to attack at the opposite, and in this case, the less hindered face. And so this will give you a trans configuration without any of the cis configuration. So having a look at the difference in reaction products between the E and Z. So in this case, the E and Z notation is used, which is perhaps a little difficult to understand how to use it, but it's more widely applicable than the cis and trans, so it's generally preferred. So you can see that both of these E and Z products, these E and Z reactants, gives you different products, so different stereochemical outcomes of the reaction. So they both go through the same mechanism, but because of the different configuration of the substituents on the reactant, it gives you a different stereochemistry of your product. And this can be explained by the bromonium intermediate. So normally this carbon-carbon double single bond intermediate would allow free rotation, but due to the presence of this bromine atom coordinating to the carbocation, it prevents rotation, and therefore it gives you a very well stereo-defined product shown here. So then looking at the problem here, you can see that you've got a cis alkene, and then under bromination conditions, you get primarily the anti-product with only a small amount of the syn product. And again, this can be explained by the formation of this bromonium intermediate, which hinders rotation about that carbon-carbon single bond of that intermediate there. And so you get selective addition of that second bromide to give the anti-product. Okay, so another related reaction to the bromination is the halohydration. So this proceeds through the same mechanism as in the first step as with the bromination. However, instead of the bromide acting as a nucleophile, it's the water that acts as a nucleophile. Since bromide is quite a poor nucleophile, and in this case, water is a better nucleophile, and this type of reaction is favoured. So again, you get the anti-addition product similar to the previous reaction. So yeah, the mechanism here is the same as before. Addition of bromine to the double bond to give you the bromonium. Then the water opens up the bromonium three-membered ring, and then the bromide can then accept a proton from this intermediate, acting as a base to give you your product and hydrobromic acid. Okay, so next we'll look at mercuration. Mercury is quite reactive with alkenes and can give you a range of products. So in this case, we're looking at alcohol products. The selectivity of the regio selectivity of the product follows the Markovnikov rules, which I believe Lydia presented previously, so I won't go into those too much further. So initially you get addition of mercury and water across the double bond, and then sodium borohydride then removes the mercury, and you're left with just the water, the alcohol. Okay, so looking at the mechanism for this, it's really quite analogous to the bromination mechanism. So again, the mercury adds across the double bond, and you form this three-membered mercury ring, which is quite similar to the bromonium shown on the previous slide. And then you get addition of water through a Markovnikov selectivity to the more substituted carbon position to give you this intermediate, and then you remove a proton using the acetate that's eliminated in this first step to give you this intermediate product. So these are stable and can be isolated. However, they're not terribly useful, and it's preferred to remove the mercury carbon bond. And this is achieved using sodium borohydride through a free radical process, which due to complexity of mechanisms, it's not shown here. So this is really typical of a number of different reactions that mercury can be used for. So again, the formation of an alcohol shown here. It can, instead of using water as your nucleophile, you can also use an alcohol. And in that case, you get your ether as a product. And furthermore, if you use a different nucleophiles such as acetonitrile. In this case, the terminal N lone pair can act as a nucleophile, and then following hydrolytic workup, this acetonitrile, which is this portion here, will give you an amide. And same reaction will be used for synthesis of amines, such as shown here, where you get addition of the amine following the Markovnikov selectivity. And then finally, this reaction can occur intramolecularly, so where the amine is on the same molecule as the alkene. And in this case, the amine then cyclizes with the alkene to give you this cyclic product. So they're really all quite the same reaction, they're just using different nucleophiles instead of water. But you can use this to get quite a range of different products. Okay, next we'll look at borane reactions. So borane can add across a double bond of an alkene. And so in this example, you form a boron carbon bond and you get donation of a hydride to the other side, the alkene. And this can occur 3 times and will give you your trialkyl boron compound. And where these types of compounds are really useful is in, again, the synthesis of alcohols. And in contrast to the mercury reactions, this follows the anti-Markovnikov selectivity. So first you form your organoboron intermediate through addition across the double bond, and then the peroxide oxidizes the boron carbon bond to give you the alcohol. And in this case, the oxidant is hydrogen peroxide, and the alcohol does not undergo further oxidation. However, if you use a stronger oxidant, such as chromium trioxide, you can get further oxidation to the ketone. And similarly, you can use a more selective borane. In this case, it's a very sterically hindered borane to get selective reduction at a less sterically hindered alkene position to give you selectively this product. And you can also access amines. And in this case, instead of using an oxidant to remove the carbon boron bond, you're using this, this oxidant here, which will then give you the amine. So quite useful reactions for giving you different products from the alkene. Okay, so another reaction that alkenes can undergo is the dihydroxylation reaction. So there are a number of reagents that can be used for the dihydroxylation of alkenes, and if you want so for selective dihydroxylation without further oxidation, the osmium tetroxide is frequently used, and the mechanism for addition is shown here. So you get a pericyclic reaction with your alkene to give you this cyclic intermediate here. And you can see that the osmium has changed oxidation state in a redox process. So from this intermediate, hydrolysis can occur with a molecule of water. and then further hydrolysis then gives you your diol. And since this reaction occurs to give you this cyclic intermediate, then the two new carbon-oxygen bonds must be on the same face of the molecule. And due to this, you get a selective syn addition of your two alcohols. So potassium permanganate is another oxidant that will react with alkenes. And you can see that it gives you a very similar cyclic structure to the osmium tetroxide. However, this can undergo further oxidations, shown here, and this can further oxidize to your hydroxy ketone compound shown here. So this this reagent's not so useful for select dihydroxylation, but it can be used for transformation to other further oxidized compounds. So this case shown here is a special case since it is a terminal alkene. And in this case, the terminal position of this alkene is oxidized all the way to carbon dioxide. And this position here is generates a carboxylic acid, as shown here. So that's an oxidative cleavage of the alkene, which is quite a common reaction. And then alkenes can also react with peroxy acids, such as shown here, to generate a epoxide. And then you get your carboxylic acid. So the peroxy acid is then reduced to the carboxylic acid byproduct. Okay, so this shows the dihydroxylation reaction of osmium tetroxide, as shown on the previous slide. And then sodium hydrogen sulfate is used to hydrolyze the intermediate to give you your dihydroxy cis-diol compound. So again, looking at the mechanism, that was shown on the previous slide. But yeah, one consideration that may not be immediately obvious is that this oxidant is not only is it toxic, but it's incredibly expensive, and use it in a stoichiometric quantity would just be impractical. And so there's a co-oxidant that's added to regenerate the osmium tetroxide. And you may remember from previous in the presentation, there was another reaction that used the co-oxidant, the tempo oxidation. So the co-oxidant again reacts with your reduced osmium to regenerate the osmium tetroxide. So in this way, you only need a catalytic amount of osmium tetroxide, and it makes this reaction more useful and practical. So the other oxidants, other co-oxidants that can be used in place of hydrogen peroxide, such as this other peroxide, T-butyl peroxide, potassium ferrocyanate, and methylmorpholine, and morpholine oxide. Okay, so looking further at potassium permanganate oxidation of alkenes, as mentioned before, that this reagent can be used for dihydroxylation reactions and goes through a similar reaction mechanism to osmium tetroxide. However, as a very strong oxidant, it tends to give you over-oxidation. And in this case, you can get further oxidation where one of the hydroxy group is oxidized to a ketone, and this may be undesired in some situations. And additionally, you can get further oxidation from the ketone to a carboxylic acid and decarboxylation to carbon dioxide. Okay, so we've looked at this first step to give you the diol, and this diol can undergo further reaction to cleave this carbon-carbon bond. So this bond between these carbons is particularly weak due to the presence of these electron withdrawing groups, and it can be cleaved through the use of another oxidant in a second reaction. So in this case, sodium periodate is used as an oxidant for the cleavage of a diol. And in this case, the diol is cleaved to give you 2 molecules of aldehyde, so from either side of this diol. So this can be a very useful way of preparing aldehydes from alkenes. And in this case, the oxidant does not further oxidize the aldehydes to carboxylic acid, so it's quite a selective method. So looking at the mechanism for the oxidative cleavage of the diol, the periodate undergoes a reaction with the diol to give you this cyclic intermediate, much like was shown for the previous examples. And this can undergo a ring opening reaction with the arrows shown in here. So it's a pericyclic ring opening reaction. And this, if you follow these arrows with the bond being broken and formed, you'll end up with these 2 molecules of your aldehyde in addition to the reduced iodine, the iodate. So there are some examples shown here, and these examples are all from cyclic compounds. So instead of having 2 molecules of product, you'll just have the one product with 2 aldehyde groups. And so from this cyclohexene, you get this dialdehyde. When the alkene is further substituted, you'll have a ketone and an aldehyde. And if you want to go directly to the carboxylic acid, so the fully oxidized form, you can use potassium permanganate. And this oxidizes it all the way through to the carboxylic acid. So another very common reagent that is used for alkene reactions is ozone. So ozone's shown here with the formula of O3. And this is a very reactive gas and can react with alkenes to give you this intermediate product called a molozonide. However, this intermediate's quite unstable and it undergoes a rearrangement to form this ozonide. And these ozonides are relatively more stable, but still, yeah, they're not stable enough to be isolated really. So these ozonides are further reacted without isolation, and they can be reacted with a reducing reagent such as zinc. And under this reduction of the ozonide, you get 2 aldehydes. So this is another way of cleaving alkene, the carbon-carbon double bond, to give you these 2 molecules of aldehyde. So having a look at the mechanism for this reaction. So first of all, ozone, this O3, is quite readily generated in the lab using a ozone generator, which is essentially just an electrical discharge through a stream of oxygen gas. So once you've generated your ozone, the structural formula is shown here. So you've got the oxygen-oxygen double bond and then another oxygen as with ion. So this can undergo a cycloaddition reaction with your alkene to give you this unstable molozonide intermediate. And this intermediate spontaneously rearranges through this two-step mechanism. And this rearranges into a more stabilized ozonide intermediate shown here. So this ozonide is then further reacted with either an oxidant or a reductant. And in this case, zinc is acting as a reductant to reduce the ozonide to give you 2 molecules of your aldehyde. So this reaction can also be performed under oxidative conditions where the ozonide is oxidized, and that in that case it would give you your carboxylic acid or ester instead of your aldehyde. So this ozonolysis can be used to access other products aside from the just the aldehydes. So if you treat your ozonide intermediate with methoxide, so deprotonated methanol, then that can react with this intermediate here to give you these 2 compounds, which then further rearrange to give you this ester. So this is, in this case, an oxidative workup and gives you an ester instead of an aldehyde, which is a more oxidized product. So there are some examples shown here. So one thing that the ozonolysis is particularly useful for is preparing aldehydes, as shown here. So this terminal alkene is cleaved, and through a reductive workup, you get your aldehyde in place with the alkene, and the other side of the alkene would simply form formaldehyde. So those are your 2 aldehyde products. Similarly, in this example, you have another terminal alkene, and ozonolysis under the same conditions gives you a ketone in this case and formaldehyde. So this example here uses an oxidative workup. So instead of using zinc, which is a reductant, they've used hydrogen peroxide, which is an oxidant. And under these oxidative conditions, instead of having an aldehyde product, you can get a carboxylic acid product. So in this case, you get this carboxylic acid, and then from the other side of the alkene, you would get formic acid. And then, as shown in the top of the slide here, you can use an alkoxide base and that can be used to generate your ester instead of an acid. So the alkenes can give you access to a wide range of different oxidized products, and can be a very selective reaction, which makes it quite useful. Okay, so looking further into the dihydroxylation of alkenes, there is potential for forming new stereocenters, much like with the bromination of alkenes and other reactions. So in this example here, where you have a terminal alkene, where one side has only hydrogens, then dihydroxylation product will give you a single new stereocenter shown here, whereas this other side of the alkene does not have a stereocenter. In this case, where it is an internal alkene, then you'll generate two new stereocenters and can give you a mixture of racemic compounds. And the outcome of the stereochemistry again is determined by the cis or trans or E and Z configuration of the alkene here. So one of the most well-known methods for dihydroxylation is the shaftless asymmetric dihydroxylation. And this can give you a single enantiomer using a chiral catalyst. So again, if you look at both of these products, you'll notice that they are both cis, where both of the alcohol groups are on the same side of the molecule, but they are mirror images of each other, and therefore they are enantiomers. So you can access each of these enantiomers by using a different enantiomer of the chiral catalyst. So in this case, they use chinchona alkaloid, which is abbreviated here. And this is a readily available source of chiral ligand. So the structure of these ligands is shown below, quite complex, but the key features are that it has a lot of steric bulk, which aids in providing stereoselectivity to the reaction. And it has these amines, both of these tertiary amines, which are able to coordinate to the osmium to form your chiral catalyst, which gives you your enantioselectivity in the reaction. And these are the two different enantiomers of this catalyst, where you just have different chiral center around each of these tertiary carbons. So having a look at the mechanism for this enantioselective reaction, the first step in the mechanism is coordination of the ligand to your oxidant. So in this case, the ligand is the large complex molecule that was shown in the previous slide. And this is able to coordinate to the oxidant through those tertiary amine positions shown. This oxidant with this chiral oxidant then reacts with your alkene in the same mechanism as shown previously. However, in this case, since you have a chiral ligand on your oxidant, then there is preferential formation of a single enantiomer of your product. Okay, so there are some examples shown here where the terminal alkene shown here gives you just a single stereocenter, but it gives you excellent EE. So enantiomeric excess is what that is abbreviation for. So that means that you have 88% selectivity for a single enantiomer over the opposite enantiomer. And then you have an internal alkene. In this case, so these reactions all use a co-oxidant, as is common for all of these osmium reactions. And this gives you 2 new stereocenters and gives you almost perfect selectivity for a single enantiomer. And this reaction can be performed on conjugated alkanes, such as this one shown here. Again, it gives you excellent enantioselectivity. Okay, so just look at some oxidation reactions again. So these are typically performed using peroxy acids, such as shown here. So the mechanism is shown below here, where you get reaction of the alkene with your peroxy acid, and you get elimination of the carboxylic acid here. And that carboxylic acid can then remove the proton from this oxonium intermediate shown here to give you your epoxide product and one equivalent of the carboxylic acid. So one of the common oxidants for this is MCPBA, so metachloroperbenzoic acid. So it's just a readily available and reasonably stable oxidant that can be used for this. So there are other methods for formation of epoxides other than direct formation, such as with the peroxy acids. And one of them is shown here. So hydrohalogenation reaction, which was shown in one of the previous slides to give you the halohydrin intermediate. And under basic conditions, you can deprotonate this alcohol, and it undergoes an intramolecular nucleophilic substitution with the adjacent bromine to give you the epoxide with elimination of a bromide. And that's the mechanism that's just shown here. So yeah, deprotonation of the alcohol and then intramolecular nucleophilic substitution to give you that epoxide ring. So as with many reactions of alkanes, you can generate new stereocenters. And similarly to the dihydroxylation, there is an asymmetric epoxidation reaction. So this is also developed by Sharpless, and the reagents used for this are shown here. So first of all, you have T-butyl hydrogen peroxide. So as a peroxide, this is your oxidant. You also have titanium isopropoxide. So in this case, the titanium is a Lewis acid and is able to coordinate ligands. And you also have diethyl tartrate. So this is a commonly available natural compound that is quite readily available and inexpensive, and therefore it's convenient to use for these asymmetric reactions. And in particular, it's easily and cheaply available as the two enantiomeric forms, the L and D. So the structure of the diethyl tartrate is shown on the bottom right here, and it's able to coordinate through the alcohol position here, and also through the carbonyl, and it coordinates to your active oxidant to give you the chiral oxidant. So this mixture of compounds gives you a active catalyst, which is quite complex and difficult to really interpret there, but you can see that you've got titanium, 2 molecules of titanium, 2 metal centers of titanium here. So that's a very good Lewis acid, and it's able to coordinate to lone pairs of electrons on the carbonyl and also through to the alcohol. And it forms this chiral complex, which gives you the chirality in the reaction. So the transition state for the oxidation is shown over here. So the catalyst then participates in the reaction to give you this transition state. So you've got your tert-butyl peroxide, which is partway through forming this epoxide bond. So you've got your alkene here, and you can see in dotted lines, these are the bonds that are just forming and breaking. And then you've got your titanium, which is also coordinated with the diethyl tartrate. And this whole complex is what gives you the selectivity in the reaction. So just looking at some examples here. So you've got a trans alkene that you're starting with, and then it gives you the oxide. And this is specific for allylic alcohols. So whereas an alcohol in the allylic position to the alkane. And so this gives you the epoxide product in excellent enantiomeric excess. And similarly with the this substrate shown here and here, they give you excellent enantiomeric excess, and these epoxides could be used for further transformations through reactions that we won't be looking at yet today. So there are other reaction conditions that can be used aside from the Sharpless conditions. And in this case, they're using a manganese ligand. So in this case, manganese acts as the Lewis acid to form the chiral coordination complex. And this takes the place of titanium in the above reactions. And in this case, the manganese is preformed as a coordination compound instead of the coordination compound being formed in the reaction mixture. And the general structure for these coordination compounds is shown here. So again, you've got coordination to the amines here, and you have a very bulky sterically hindered substituents, which help to give you a better selectivity for the single enantiomer. Okay, so finally for the oxidation section, we'll look at a special situation where ketones can be oxidized further. So the oxidation of a ketone, so the Baeyer-Villiger reaction is the oxidation of the ketone. And the types of products it gives you is an ester. It can give you an ester from an acyclic ketone, or from a cyclic ketone, you can give a lactone, which is just a cyclic ester. So the mechanism for this reaction is shown on the right-hand side here. So the first step is activation of the carbonyl by protonation. And after protonation of the carbonyl, you can get nucleophilic addition. So the nucleophilic addition is by the peroxy acid anion, and it adds to the carbon position of the carbonyl to give you a tetrahedral intermediate. So the tetrahedral intermediate is shown in here. And this intermediate undergoes a rearrangement. So the lone pair from this alcohol goes back in here to reform the carbonyl, but instead of loss of a proton, as you would have in other oxidation mechanisms, you instead get a shift of an alkyl group. So you get a carbon-carbon bond that shifts across to become a carbon-oxygen bond. And then you get elimination of your carboxylic acid, as shown here. And so if you follow all the new bonds forming and breaking, you'll see that you get an ester forming in addition to your carboxylic acid that is derived from the peroxy acid oxidant. And then you get removal of the protonated carbonyl, and that gives your product there. So this can be a very useful reaction for expanding the range of products that can be accessed from simple oxidation reactions. Okay, so moving on from the reduction, moving on from the oxidation part of the presentation, I'll be looking at reduction reactions. So some of the common reducing reagents are listed here. And you'll note a common feature for all of these is that they have a hydride that can be donated. So by transferring a hydride, you are reducing your compound. In the top case here, the hydride is transferred from hydrogen, and that is catalyzed by transition metals such as those shown here. And then you can have some metal hydrides, which are very common reductants. And this top row here are some of the stronger metal hydrides, which can reduce a wide range of compounds, with this one being particularly strong, this lethal. And then moving down, you can get boron hydride reagents. So these are generally milder reagents for reductions and very commonly used. And then these are also borohydride reagents. And then this one here is a silane. So in this case, the silicon hydrogen bond can act as a hydride donor and can therefore act as a reductant. And then there are some other less frequently used reducants, such as sulfides. So sulfide can act as a reductant, and some others. Okay, so first of all, we'll look at the so hydrogen is always used in combination with a transition metal catalyst, often palladium, and can be used to reduce double bonds and triple bonds. So the triple bond can reduce all the way to the single bond. The double bonds can be reduced to the single bonds, or under selective conditions, the triple bond can be reduced selectively to the double bond, and this will give you the cis alkene. And since this selective reduction of an alkyne to an alkene gives you only the cis alkene, another method to access the trans alkene from the alkyne is a dissolved metal reduction. So in this case, lithium metal can dissolve in ammonia gas, and this dissolved metal can donate a single electron to your substrate. So in this case, so it's a single electron transfer mechanism. And this is useful and is complementary to hydrogenation shown here, since it will give you the trans or the E alkene. Okay, and looking further into the reduction of alkenes, a special case is in the reduction of conjugated alkenes. So this is where the alkene is in conjugation with an electron withdrawing group, such as a ketone shown here. So if you look at reducing this type of substrate, the reduction can occur through two different mechanisms. You can either have a 1,4 reduction. So this is where the hydride is donated through a 1,4 type of mechanism. So the 1,4 comes from the numbering of the atoms. So if you can imagine 1, 2, 3, 4, so then the reaction occurs across the 1 to 4 positions. Alternatively, the reduction can occur through a 1,2 reaction to give you the alcohol. And this is a 1,2 because you have the numbering the atoms, it's just 1 and 2. So, and in addition, you can get it fully reduced down to the aliphatic alcohol. So if you imagine the 1,4 reduction product, this can then undergo further reduction to the alcohol. So we looked at sodium borohydride previously, but this is not very selective for these types of substrates, since it tends to give you a mixture of both the 1,4 and the 1,2 reduction. So generally you'll have a mixture of compound B and C, but that's dependent on the substrate's steric and electronic effects. So having a look at some more selective reductants. If you want to have selectively the 1,4 reduction, so just reduction of the double bond without reduction of the carbon-carbon double bond, without reduction of the carbonyl, then you can achieve this through simple hydrogenation using palladium on carbon. Since these reductive conditions do not generally affect carbonyl groups. Alternatively, if you want addition of the hydride through a 1,4 addition mechanism, then what you need is a soft metal. So if you remember the hard-soft acid-base theory, then addition through the 1,4 mechanism requires a soft nucleophile. And so to achieve this, you can use copper hydride, since copper is a very soft metal and favors the 1,4 reduction or 1,4 addition reaction. So there's some examples that are found shown here. So you have the enone, and then using Stryker's reagent, you can get selective reduction of the carbon-carbon double bond. And also, in this case, they have good stereoselectivity. And on this more complex molecule here, this would not be suitable for hydrogenolysis, for hydrogenation reaction, since you would reduce this alkene in addition to the enone. And so they've used Stryker's reagent to selectively reduce the carbon-carbon double bond without reducing either the carbonyl or the alkene. So much more selective reagent. So in comparison, if you wanted to reduce only the carbonyl and not the alkene, so 1,2 reduction, then by far the most commonly used reaction is the Lusch reduction. So this is a combination of cerium chloride and sodium borohydride. So again, thinking about hard soft acid base, you need a hard nucleophile to favor the 1,2 addition. And in this case, cerium chloride is used because it's a very hard Lewis acid and coordinates to the carbonyl and favors reduction, 1,2 reduction with sodium borohydride. So this is a very practically useful reaction condition to give you access to allylic alcohols, such as shown here. Okay, so just looking at some reducing agents. Some more reducing agents for carbonyls. So yeah, the ketone can be reduced to secondary alcohol, aldehyde to primary alcohol, and they usually require only very mild reaction conditions. These aldehydes and ketones are quite reactive towards hydride reductions. So the carboxylic acid can also be reduced either to a carbonyl, aldehyde. However, that aldehyde, if it's not selective, that aldehyde will be further reduced to the primary alcohol. And this, yeah, the reduction of an acid generally will give you the alcohol, and so there are more selective methods for accessing an aldehyde from a carboxylic acid. And one of the best methods for that is first to transform your acid into an ester. And the ester has quite different reactivity to the acid. And a lot of that is due to the acid having an acidic proton, whereas the ester does not. So there are a number of reagents that can be used to reduce the ester selectively to an aldehyde. You can also activate the carboxylic acid through other derivatives, such as an acid chloride, so where X is a halogen. And then again, there's a number of reaction conditions that will selectively reduce the acid chloride to an aldehyde without unwanted reduction to the alcohol. And then as another set of reactions, you can reduce the carbonyl all the way to its fully reduced form, which is just an alkane. So transforming that carbon-oxygen double bond to just 2 carbon-hydrogen bonds. And there are some named reactions such as Clemmensen, Wolff-Kishner, and thioacetal reactions, which can achieve this. So first of all, just looking at reduction of ketones, this can be achieved using borohydride reagents. So in this case, BH4 is the borohydride anion, and that so the metal, so the counter ion, the metal coordinates to the carbonyl oxygen, which activates the carbonyl, and then the carbonyl then undergoes a reaction with the borohydride to give you a boronate complex with your alcohol product. And this complex is readily hydrolyzed on workup to give you the alcohol product. And again, with aluminium hydride, the mechanism is identical, and you can, because boron is directly above aluminium on the periodic table, it's has very similar chemical properties, and so participates in similar reactions. Okay, so looking into more detail on the reduction of carboxylic acids, lithium aluminium hydride, which is the strongest commonly available hydride reducing agent, that is capable of reducing the carboxylic acid all the way to the alcohol, but it would not be possible to stop this reaction at the aldehyde stage. And in addition, this reagent would react with many other functional groups, which you may not want it to. Looking at a much milder reducing agent, sodium borohydride, this will give no reaction with the carboxylic acid. And this can be explained by the deprotonation of this acidic position, which then deactivates the substrate towards further reaction, where the borohydride is just not strong enough to reduce it. So some ways to work around this. So if you don't want to use lithium aluminium hydride because it's not compatible with your compound, it will reduce everything, but borohydride's not strong enough to reduce your acid, then the ways around this is to derivatize your carboxylic acid to something such as a halide, acid chloride or an ester. And both of these derivatives are capable of being reduced by sodium borohydride. The ester, however, if you look at some other borohydride reagents, such as cyanoborohydride shown here or triacetoxyborohydride, these are deactivated reductants in comparison to the sodium borohydride. So they're much less reactive as reducing agents and therefore are not capable of reducing the ester. However, the acid chloride is more activated as a carbonyl and therefore does undergo reaction with these deactivated reagents. So there's a lot to think about there, but you got to think about the balance between how readily reduced your carbonyl is and how strong of a reductant your reducing agent is. And so these reagents shown here, they're not capable of selectively forming a aldehyde, since the aldehyde readily reacts with the reagent to further be reduced to the alcohol. However, there are some methods for selectively forming a carbonyl aldehyde from an ester, such as shown here. And one of these reagents is diisobutyl aluminium hydride, or abbreviated DIBAL more commonly. And the way this is able to selectively reduce the ester is that it undergoes it transfers a hydride to your substrate to give a hemiaminal type of structure, but this hemiaminal is coordinated to the aluminium, and this coordinated complex is stable at low temperatures due to the steric bulk of the diisobutyl position. And therefore, if you keep the reaction at low temperatures, then you can selectively form the aldehyde without over reduction to the alcohol. But in practice, it's not always that easy. Okay, so looking at other carbonyl compounds, the primary amide shown here readily reacts with lithal, and this reduces the carbonyl all the way down to an amine. So you're forming two new carbon-hydrogen bonds and removing that carbon-oxygen double bond. In contrast, sodium borohydride is not strong enough to perform this reaction. And again, lithal, which will reduce just about anything it can, will also reduce a nitrile, so a carbon-nitrogen triple bond. And in this case, it will add the hydride to that carbon twice, and you'll end up with an amine. So you're forming two new carbon-hydrogen bonds there. And again, DIBAL can be used to selectively reduce substrates to aldehydes because it forms a stable complex at low temperatures, which prevents over-reduction. So in this case, the primary amide here is reduced to a aminal intermediate, which is complexed with the aluminium. And then on workup, that aminal is hydrolyzed to give you the aldehyde. And similarly, the nitrile can be selectively reduced to an imine, so a carbon-nitrogen double bond instead of a triple bond. And that type of functional group can be hydrolyzed to an aldehyde. So those are two ways of selectively accessing an aldehyde. But yeah, it requires low temperature, and often the over-reduction product is formed to some extent. Okay, so moving on, we'll have a look at reductive amination. So this is probably one of the most widely used methods for synthesizing amines. For a reductive amination, you initially form what's known as an imine. So reaction of an amine with a carbonyl compound will give you a condensation reaction to form this carbon-nitrogen double bond where there was a carbon-oxygen double bond before. And then these imines are much more readily reduced, so much more reactive than aldehydes or ketones, and they are reduced in a similar way by addition of hydride to that carbon position, and then that gives you your amine. So there are different types of amines that will give you different amine substitution patterns. So you can have no substitution on the nitrogen of that amine, and that will give you a primary amine. You can have a single substituent on the amine functional group, and that'll give you the secondary. Or you can even have two substituents on that amine nitrogen to give you the tertiary amine shown here. So yeah, where this type of reaction is most used is in reductive amination procedures. So these can be done as one pot. So that means the isolation of amine is not necessary, and you just mix all of your reactants and reagents together. So you've got your amine and your carbonyl, which undergoes a condensation reaction to give the amine, and that is reduced using one of the soft reducing reagents. So quite often the deactivated boron hydride reagents shown here, and that will reduce the amine down to the amine. So there are a couple of things that can go wrong with this type of reaction. So you might note that your carbonyl starting material is capable of being reduced, which would just give you the alcohol instead of the amine. But in this case, because you're using these deactivated reagents, your carbonyl is not reactive to what's being reduced, and it's only once it's formed the amine that it can be reduced, and will therefore give you your product. Another issue is that your product, being an amine, can then go through another cycle of the reaction. So you can imagine this product would react with your carbonyl again to give you another amine, and then it would get reduced again, and this would give you another substituent on the amine to give you a product that you may not want. But there's some tricks around that. Yeah, it can be some reactions are better than others. All right, moving on to reduction of a carbonyl down to a methylene, so a CH2 group. One of the most well-known methods for this is called a Wolff-Kishner reduction. So got your carbonyl here, and it reacts with hydrazine under basic conditions with a lot of heat and strong base, and it completely reduces your carbonyl down to a CH2. So just having a look at this mechanism, Similar to the reductive amination, the initial step in this reaction is condensation of your, instead of an amine, it's a hydrazine, but condensation of your nitrogen compound with the carbonyl. So condensation reaction here, and this gives you your carbon nitrogen double bond, so much like the amine. But in this case, we don't have any borohydride reagents, so that amine type compound's not reduced. And instead, under the strongly basic conditions, you can get removal of a proton from this position. So this, yeah, it's not an amine, it's a hydrazone, but yeah, like an amine. But yeah, you get removal of this proton from this position and transfer of electrons into this nitrogen-nitrogen bond. And then you get effectively transfer of a proton to this, this carbon position from this nitrogen. And that gives you this type of intermediate here where the double bond is shifted from being here to being between the two nitrogens. And then a second deprotonation then again moves electrons into this nitrogen-nitrogen bond, and you get electrons here moving onto that carbon atom to give you a carb anion. And if you notice here, you're forming nitrogen-nitrogen triple bond and breaking those two other bonds, so you're actually forming nitrogen gas, which is a really strong thermodynamic driver of these types of reactions. And so this carb anion, which is a fully reduced product, can then be reprotonated from water in the reaction mixture. And so you're left with just your fully reduced alkane methylene compound with loss of nitrogen. So a couple of examples would be, yeah, so we've got an example here where you have benzophenone. I use microwave irradiation, so very, very hot, very high reaction temperature. And generally these types of reactions require very high temperature to proceed. So not very good, not very tolerant of other functional groups that may react. So yeah, initially they form the hydrazone, and then under further microwave irradiation, they get the Wolff-Kishner reduction, form this product, and this reaction is really probably favored because that carb anion that you form at that position is stabilized by both of these aromatic rings. So it's the kind of reaction that's not that widely applicable. So another method for reduction of carbonyl compounds to methylene compounds is the Clemmensen reduction. And this utilizes a zinc mercury amalgam. So it's mercury metal that dissolves other metals, and you get an alloy of mercury and zinc. So the mercury really helps to activate the zinc as a reductant in this case, and then you use HCl for acidic conditions for the proton donation. So this reaction mechanism proceeds through a single electron transfer mechanism, so SET. And that means that it's a radical reaction. So initially you get transfer of a single electron to that carbon of the carbonyl, and you generate this radical anion intermediate. And that anion is then protonated and additionally, there's a second electron that is transferred. So there's two single electron transfer steps that occur there. So then the zincate species here can undergo substitution with a chloride, and you get elimination of that that zinc hydroxy compound to give this chloro alkane intermediate, and then reduction again with another single electron transfer process gives you another radical, and then another addition of another electron to give the carbanion, and protonation gives you the product. So in this case, the reaction is really strongly favored due to stabilization of the anion, the radical intermediates, since each of these radicals are at a benzylic position, since you've got a phenyl ring here. So that is probably quite important to the success of this example. So they've got an example shown here where there's a fairly complex molecule. So you'll notice there's a ketone here, and in addition there is a amide here. So if you think about some of the other, like the Wolff-Kishner reaction that was on the previous slide with hydrazine, the hydrazine being a very good nucleophile would likely react with your amide, and so it's not really compatible with this type of substrate. So they've used the Clemmensen reduction in this case and achieved a reasonable yield of their reduced product without having any effect on the amide. A third method for reduction of a carbonyl compound down to its methylene product is through formation of a thioacetal followed by reduction using nickel. So thioacetals are just a cyclic compound. It's just a condensation of a dithiol, in this case ethane dithiol. So you've got a thiol on both ends of the ethane, and this undergoes a condensation reaction with a carbonyl. So through a familiar mechanism, you get addition to the carbonyl to give you this tetrahedral intermediate, and this can be protonated. This alcohol on this intermediate can be protonated under acidic conditions, making this H2O a good leaving group. And one way of drawing this is the lone pair of electrons from that sulfur moves in here and eliminates water to give you this charged sulfur intermediate. And then again, similar to addition to a carbonyl, you get addition of the thiol to that sulfur carbon double bond and gives you the thioacetal. So this thioacetal can be reduced using Raney nickel. Nickel has a fairly unique property as being very good at desulfurization reactions, where it reduces sulfur-based compounds and nickel sulfide is produced. So the conditions for this is a stoichiometric amount of the rainy nickel and ethanol. So this is probably the more favored reaction, since it's pretty mild reaction conditions and doesn't use mercury. So yeah, some of the other considerations for these reactions are that the Wolff fission is basic and very strongly nucleophilic. The Clemmensen reaction is under acidic conditions. The thioacetal reduction is neutral. So this is important to consider where other functional groups on your molecule might be sensitive to basic or acidic conditions. Okay, moving on, we'll look at reduction of nitro functional groups. So this is a very common reaction, since the aryl nitro group is quite easy to introduce through a nitration reaction, and the aniline product is useful for a wide range of transformations. So some of the reducing agents are shown here. So the mildest one would be just palladium with hydrogen gas. You can also use other transition metals with hydrogen, such as nickel. And then looking at other methods, these would include zinc or iron based reductions, but these types of metal-based reductions require some acid. So they're frequently used in combination with acetic acid, or occasionally hydrochloric acid or ammonium chloride. So you just need some proton source. And it's the same with tin chloride. It's quite an acidic, so it's a Lewis acid, and so therefore fairly acidic. And then you can also use sulfides. However, they have an unpleasant smell, so they're not commonly used unless you have to. And another important thing to note for reducing nitro compounds is that it's only the aromatic nitro groups that are generally reduced, especially with these types of conditions. They will only reduce the aromatic nitro groups, and reduction of an alkyl nitro group requires a bit more specialized reaction conditions, since it can give you products other than the amine. It can give you things like such as a hydroxyl amine, which may not reduce further to the amine. So palladium with hydrogen gas is a really mild method for reducing nitro groups, but you also have to think about what else it could be reducing on your molecule. So in this case, they have a aryl bromide group as well as the aryl nitro group. And not only would this palladium with hydrogen reduce your nitro, it will also remove your aryl bromide. And this is probably not something that you want to happen. So in this case, you would be, you'd have to rely on some of the metal-based reductions as shown on the right-hand side here, such as tin chloride, which are very selective for reduction of nitro groups. Okay. So looking at other reductions of alcohols and alkyl halides. So if you want to reduce your carbonyl all the way to the CH2 fully reduced form, you can do it in one step using the methods presented before, but alternatively, you can do it in a two-step reaction where you first reduce the carbonyl to an alcohol, and then you can functionalize that alcohol as a very good leaving group. And by converting that alcohol to a leaving group, then it is more easily reduced down to the CH2 fully reduced form. So in this case, the alcohol is converted to a sulfonate, similar to an ester, but with a sulfonic acid. And this sulfonate is particularly good as a leaving group, since the sulfonate anion is very stabilized. And as a good leaving group, it can be also reduced using a strong reductant such as lithium aluminium hydride. So there's a number of different sulfonate functional groups such as tosylate or mesylate, which are just abbreviations for toluene sulfonate or methane sulfonate. And these sulfonates, you can imagine them as being very similar to alkyl halides such as chlorides or bromides. And the similarity is really since they're both very good leaving groups and can therefore be reduced under similar conditions to shown here. So again, looking at, so that this is really applicable to alkyl halides. But aromatic halides are different in their reactivity since they do not undergo nucleophilic substitution reactions and just different reactivity. So as shown before, the aromatic bromide or iodide can be reduced using palladium with hydrogen. The fluoro is quite unreactive, very stable, and is not generally reduced under those conditions. The chloro is intermediate reactivity, and in my experience, it can be reduced under those conditions, but it's really dependent on the substrate. But if you switch to a different metal, such as rainy nickel, then it can have different reactivity as a reductant, and therefore is less likely to reduce your aromatic halides. So aside from using hydrogenation to reduce aromatic halides, another option is through a organometallic reagent. So in this case, this is applicable to both alkyl and aromatic halides and really is dependent on the formation of your organometallic reagent. So Grignard reagents, probably everyone's familiar with, and they can be readily formed using alkyl or aryl halides to give you this organometallic intermediate. And that's a useful intermediate for reaction as a nucleophile with a lot of different things, but it can also react with water or other proton sources such as an alcohol and get protonated with loss of your metal as a salt. So in this case, H2O is acting as a proton source. So it's donating H+ to your metal carbon bond to give you your reduced product. And it will also give you some metal hydroxide salt. So yeah, there's a few options there for reducing aryl halides and alkyl halides. But it's really, you have to look at the substrate to see what's suitable or best used. Okay, so other ways of reducing alcohol or OH compounds is through the formation of a benzyl ether. So benzyl ethers have a benzylic position that is quite reactive towards reduction. So it hasn't drawn out the formula. I haven't got the formula drawn out here, but if you imagine the benzyl alcohol with just an alkyl substituent of that alcohol, and yeah, they can be quite readily reduced under standard conditions, and that benzyl ether will be, well, in this case, so benzyl ether, this one's a benzyl amine, but it's reduced similarly, but the benzyl ether is reduced to toluene, so it's another deoxygenation reaction, and then you're left with your free alcohol, and that's a very mild reaction and is useful for some compounds difficult to work with, such as these. And you can also reduce just the benzyl alcohol, such as this one here, through hydrogenolysis conditions. And it gives you this deoxygenated product where this carbon-oxygen bond is removed and replaced with just the carbon-hydrogen. So yeah, that's the benzyl ether shown here. And that gives you your alcohol. So the carbon-oxygen cleavage will always happen at the benzyl side, leaving the ROH, so leaving the other side, the other carbon-oxygen bond untouched. And that will give you toluene as a product and your alcohol. And looking at this substrate here, you've got 4 benzyl ether groups, but you've also got a methoxy, so a methyl ether group. And under these conditions, only the benzyl groups are reduced and the methyl ether is untouched. So it's quite a selective method for protecting and deprotecting alcohols. Okay, then if you're looking at, we'll have a look at reduction of aromatic rings. So aromatic rings, due to their aromatic stability, generally under standard conditions, they remain untouched, but you can use some special reaction conditions to reduce aromatic rings, in particular for this one, a benzene ring. So this is known as a Birch reduction. And the reaction conditions are shown up here just with a simple benzene ring. And this gives you a cyclohexadiene. And it gives you specifically in a 1,4 isomer. So the 1, 2, 3, 4. So it's a 1,4 cyclohexadiene. And this reaction relies on the use of sodium dissolved in ammonia. So similar to the reaction for reduction of an alkyne to a trans alkene, you can dissolve this metal in liquid ammonia, and you also need to have an alcohol in the reaction mixture as a proton source. So the mechanism is shown here, and like some of the other mechanisms, it's a single electron transfer mechanism. So this dissolving sodium in ammonia, you actually have a solvated electron, so you have free electrons in the reaction solvent, which are able to react with your aromatic ring. So this arrow here is a half arrow, which signifies that it's only a single electron being transferred here. And then you get the double electron being transferred across over to here. And so you have a carb anion at this position and a radical at this position. So the carb anion is protonated by a proton transfer with your alcohol. And then that gives you another hydrogen on that position. And your radical at the other side can then accept another electron. And so by accepting another electron, then you get a full valence shell and another carb anion produced at that position, which then gets protonated by another equivalent of your alcohol to give you the cyclohexadiene. So the reaction products can be a little more complicated when you're looking at substitution patterns on the aromatic ring. So in terms of where these two double bonds, they're always going to be in the 1,4 configuration, but they can appear at different positions around the ring depending on the substituent. So looking at the electron-rich substrate, this anisole, they get the more substituted alkene. So shown here. So this is in contrast to if the methoxy substituent was at the allylic position, which is not observed in this reaction, since the more substituted alkene is stabilized in this case through resonance. And then again, looking at this disubstituted electron rich substrate, you get the more substituted alkene forming instead of having any of these constituents at the allylic position. And then under these reaction conditions, you can also get reduction of conjugated alkenes, such as shown here, in addition to the Birch reduction, and that gives you this product here. Okay, so if you want to go even further and reduce your benzene ring all the way to a cyclohexane, you can accomplish this using hydrogenation conditions. So using hydrogen gas in conjunction with metal catalysts such as nickel, rhodium, palladium, platinum. But due to the aromatic stability of this benzene ring, it requires pretty extreme temperature and extremely high pressure of hydrogen. This makes it really impractical and a little bit dangerous to perform on a lab scale, but it's performed on industrial scale a lot. So just having a look at an example from literature here, they've got so the Y can be a CH or a nitrogen, so that would be a benzene ring or a pyridine ring. And using this rhodium catalyst, they use 5 atmospheres of hydrogen, which is a really extreme pressure and requires very special apparatus. And they also do it at 80 degrees. And they fully reduce that aromatic ring right down to the cyclohexane or piperidine ring. And this can also be done on other compounds such as furan to give you the tetrahydrofuran product. Okay, so that's the end of my presentation for today.
Okay, thank you, Ian. It's very interesting and details cover all of the organic reaction related to the oxidation as well as reduction. So there are a lot of questions already here in the chat box, but before I read the question, maybe the student also can raise your hand and ask directly to Ian's. Okay. Okay, here we have Raihan. Raihan, okay.
Hello.
Hi.
Okay. Hello, Mister. I have a question for slide number 11.
Okay.
For slide number 11.
Just a second.
Yeah, it's right. It says here that one metal oxidized into carboxylic acid. What happens if metal, we have 2 or 3 methyl or paradimethyl benzene? Will it oxidize into both 2 decarboxylic acid or just one or else? Thank you.
Yeah, that's a good question. I think it really depends on the reaction conditions. So, of course, you could get 2 subsequent oxidations if you just continue the reaction for longer, or maybe increase the amount of oxidant or reaction temperature. One interesting thing about that question is if you had a 1,4 dimethylbenzene, then the first one will be oxidized to the carboxylic acid, and that actually deactivates the aromatic ring and makes the second oxidation perhaps a bit harder, just as in this case. So carboxylic acid would be deactivating similar to the nitro group. So I think you could get either product just depending on your reaction conditions.
Okay, is it clear, Rehan?
Yeah, understandable. Thank you very much, sir.
Okay, is there anybody else? Okay, maybe we can move to the chat box here. Actually, since we have a lot of oxidation and reduction reagents, so there are 2 questions. I think it is maybe we can Ian can ask directly about the criteria for choosing either the oxidation or reducing agent. So what is the best consideration when we want to choose a particular reagent for this kind of reaction?
So I think really you have to look at what other functional groups are on the compound that you're trying to perform the reaction on. So if it's a very simple molecule without any other functional groups other than the functional group you want to react, then you can really choose whatever reagent you want. And from a practical point of view, that's probably what you're familiar with or what you've had success with previously, or just what's convenient. But then where it gets a little more complicated is when you have a complex molecule with many different functional groups, and you really have to understand how each of the different reagents is selective for performing the reaction that you want and not giving you any side reactions that are unwanted. So there are a lot of reagents there, and it's not something that you can really memorize, but you just, as you go through doing problems and questions, you do get more familiar with the different reagents that are available. But yeah, it's mainly to do with selectivity and if it's compatible with your compound.
Yes, okay. Yeah, I think it is clear, right, for Sultan and Dimas, right? Okay, Rehan, do you still have a question or want to speak, or okay, maybe not. Okay, maybe we can move to the next question here about instead of titanium as the metal catalyst to perform the F-oxidation, is there any other alternative?
For the F-oxidation, that was the enantioselective, yeah, that one. So yeah, one of the metals that has been used is shown here, the manganese, and there are probably a lot of other metals that have been used for this purpose. So you'd really need a transition metal which is able to form a complex with your chiral ligand, and then that would give you the enantioselectivity. So yeah, they've used manganese here, which is able to form a chiral complex similar to the titanium. But yeah, I'm sure there's a lot of transition metals that have been used.
Okay, I think it is clear, right? Okay, for Siti Safira. And the next is from Rachelia Salsabila. She asked about the Swern oxidations. Which electrophile is the best for DMSO to get a good probably conversion in this Swern oxidation?
Yeah, that's a good question, because there are quite a long list of electrophiles that are given here. And one of the important consideration, well, one thing that's not listed here, but is really critical with, in particular, the Swern oxidation, is that if you let the reaction temperature rise above this -78, which is really quite cold, if it rises much above this temperature, you can get other reaction products. So you get rearrangement of this type of sulfide, and this will give you products that are not useful. And this is actually not the same. The requirements for reaction temperature is not actually equal for all of these electrophiles. My preferred electrophile is sulfur trioxide. It's got a named reaction for it, the Parek-Doering reaction. And with the sulfur trioxide, it only requires reaction temperatures at 0 degrees, so it's much more convenient to use, and it gives you much less of the side product. So I think that's the best use.
Yeah, okay. Related to the handling specific condition of reaction, we have another question here about the handling the radical, free radical pathway during the oxidation. How we can perform this kind of reaction technically? Is there any special condition during the reaction? This is the question of Vista, I think, yes?
How you can perform it? What, sorry? Sorry, could you repeat?
Yeah, this is about the oxidation involving free radical pathway. So technically, is it involving special condition during the reaction?
Well, nothing in particular. Yeah, so the free radicals, obviously, they can be very highly reactive. So do you know which reaction that was? Was it this oxidation or?
Yeah, kind of oxidation with the free radical mechanism.
Okay. Yeah, the free radicals, they can be very reactive. So they can give you a lot of side products, but yeah, they can also give you very good selectivity. There's not any special reaction conditions. It's choosing the right reaction, and yeah, sometimes you just have to try it and see if it gives you the product that you want. But yeah, the radical reactions often are not very selective, and that's quite clear with radical halogenation reactions, which we haven't looked at. But yeah, I don't know if that answers the question.
Yeah. Okay, since we still have a lot of questions, but the time is maybe almost finished in 6 minutes. So I move to the other question regarding the reduction here about relatively low reactivity of sodium boron hydrate compared to the lithium aluminum hydrate. What solvent that is suitable, as the sodium boron hydrate is the reducing agent?
Yeah, so the difference in reactivity, you can look at it in terms of difference between the aluminium hydride versus the boron hydride. So aluminium's probably it just gives you a different reactivity in terms of its ability to donate hydride to your substrate. And in addition, there's the lithium aluminium hydride has lithium, and so that can coordinate to your substrate and enhance reactivity. So they're just fundamentally different reagents. Yeah.
Okay. Yeah. Next is about the imine pseudo-activated carbonyl. Here is a question from Aisha. So why does it require soft reducing agent only? And what will happen if we use moderate or strong reducing agent?
Yeah, so the imine is capable of being reduced by a wide range of reductants because it is very reactive. And so you don't necessarily need a soft reducing reagent to perform this reaction. You can use any hard reducing reagent and it'll still give you the amine. The main reason for using the soft deactivated reagent is so that you can perform the one-pot reductive amination. So if you used a strong reducing agent, it would reduce your carbonyl before it had a chance to react with the amine. So in that case, you'd just end up with a mixture of your alcohol and your amine, which is not so useful.
Okay. Yeah. Maybe it is the last question, I think, because the time is already off, from Muhammad Rashipari. So regarding the Bayer-Villager reactions, I've read on several online sources about the migratory aptitude of the reaction is ranked as the following: tertiary alkyl, then secondary, aryl, and primary alkyl. What are the factors that affect the migration ranking order?
So if you look at the mechanism here, which is the key rearrangement step, this R1 group has to migrate across to the oxygen. And the transition state with this would give you a partial positive charge at that R1 group. So if you can have substituents there which stabilize the carbocation, then it will more easily migrate across to that position. So stabilization like through conjugation or secondary, tertiary carbons, that kind of thing.
Okay. Yeah. I guess it's already clear and really comprehensive. Even though this question are still a lot here, but I hope the student can also later on discuss more with us or maybe with Ian also through email.
Yeah, I'm happy to receive questions.
Yeah. Okay. Okay, thank you very much again for the nice lecture today, Ian, and dear audience. Before we close this session, maybe we will have a photo session. Just maybe you can open your camera. Okay. Okay, the student, you can try to open the camera and okay, maybe we have here 4 pages. So okay, let me start the presentation. First one. Okay, and then second. One. And last. Okay. Okay, once again, thank you very much, Jan. And nice to meet you. And we hope we can join again in another occasion later on.
Oh, yeah,
Yeah, that was great. Thank you for the
the
opportunity.
conference. Yeah. Thank you, Ayan.
Okay.
Okay. Bye.
Bye-bye. Have a nice day.
Have a
Yeah,
nice
you too.